Welcome back, everyone. Ready for another deep dive?
Always.
Awesome. So today we're taking a look at 3D part segmentation.
Oh, interesting.
Yeah. You sent over some seriously cool research on it, specifically this paper, SAMPart3D, segment any part in 3D objects, and it's pretty mind-blowing stuff. I mean, this research could totally change how we understand and interact with, like, 3D objects in all sorts of fields. So get ready to unpack some seriously complex concepts, but we'll break it down so we can all like wrap our heads around it and really appreciate the cool stuff that's happening here.
Yeah, I think what's really exciting about this is trying to solve a really fundamental problem in computer vision, which is really teaching computers to see 3D objects in the way that humans do.
Yeah.
You know?
It's so true. We effortlessly recognize like the different parts of an object, like the legs of a chair, the wings of a plane.
Right.
But for a computer, that is incredibly difficult.
It's super hard. And, the traditional methods that we've had, they kind of struggle with this because there's just so much variety in 3D objects out there. And they've really relied on these massive data sets where every single part is painstakingly labeled by like humans.
That sounds tedious.
Oh, it's so expensive and time consuming. And then even then they struggle with new objects that they haven't been specifically trained on.
Right.
So there's a real need for something new, something.
Exactly. And that's where this whole SAMPart3D thing comes in, right?
Yeah.
So instead of needing all those pre-labeled examples, this framework uses something called zero-shot learning.
Yeah.
And it basically can draw insights from these massive unlabeled data sets like Objaverse.
Right. Yeah.
So it can adapt to new objects and scenarios without needing like tons of manual labeling.
And Objaverse is incredible. I mean, it's got like over 800,000 3D objects, all sorts of different things. So it's giving SAMPart3D a really broad understanding of 3D shapes and all the different parts they can have.
Wow. So, okay, it's learning from this massive 3D library. But how does it actually break down an object into its parts? Like how does that work?
Well, the paper outlines 3 key stages.
Okay.
And the first one is large scale pre-training. This is like the foundation.
Okay.
Imagine showing a computer thousands upon thousands of 3D objects. Like you're teaching it to see in 3D.
Right. So it's building that basic like fundamental understanding of 3D shapes.
Exactly. It's learning to recognize patterns and extract the features that are meaningful. And what's really cool is that it does this by actually leveraging the power of existing 2D image recognition models.
Oh, interesting. So like it's taking what we know about analyzing 2D images and applying it to this more complex world of 3D.
Exactly. And one of the models they use is called DINOv2.
Okay.
And they're adapting it for this 3D world.
Clever. So what happens next? Like once it has that basic understanding?
So the next stage is called sample-specific fine-tuning. And this is where the computer zooms in on a specific object that it needs to segment.
Okay. So it's taking that general 3D knowledge and actually putting it to use.
Yes, absolutely. And they use this lightweight component called an MLP, and it gets trained to group points on the object into parts that make sense.
Okay.
And what's really remarkable is that they have something called scale conditioned grouping, which means that the computer can actually control the level of detail in the segmentation.
Oh, wow.
Yeah.
So like it can segment the whole chair leg or just the foot at the bottom?
Exactly.
Oh, that's fascinating. I'm like picturing those adjustable magnifying glasses,
Right.
zooming in and out to see different levels of detail.
That's a great analogy.
Cool.
Yeah, the computer can adjust the level of detail based on what's needed.
Okay, and then we come to the final stage, and this is kind of the most mind-blowing part.
Okay, lay it on me.
It's called semantic querying with MLLMs. Okay, so here's where those multimodal large language models come in. I know they can understand both images and text. So how do they fit into all of this?
So at this point, the computer has grouped the object's points into parts, right?
Right.
But it doesn't necessarily know what each part is. It can't say this is an arm or this is a wheel. And that's where the MLLMs come in. They act like expert labelers. They analyze images of the parts, and then they provide human readable names for them.
Wow.
Yeah.
It's like the MLLMs are giving the computer a vocabulary for the 3D world.
Exactly.
That's incredible. So we've talked about all these stages, and it sounds really cool in theory, but how do we know if this actually like works? Like, how did they test SAMPart3D?
But they needed a good challenge.
Yeah.
So to really put SAMPart3D to the test existing data sets for 3D part segmentation, they were just too simple.
Right.
So they created their own.
Whoa.
Yeah, they called it PartObjaverse-Tiny.
They built a whole new testing ground.
They did.
Wow, that's dedication. Okay, so what's so special about PartObjaverse-Tiny? What makes it different?
Well, it's a collection of 200 3D objects, but they're really complex objects.
Okay.
And they have these really detailed annotations for both semantic and instance segmentation.
Hold on. Can you remind me, like, what's the difference between those two again?
Oh, yeah, of course. So semantic segmentation, that's when you're labeling points on an object by their category. So, for example, all the points on a chair leg would be labeled chair leg.
Okay.
But instance segmentation takes it a step further.
Okay.
It labels each individual chair leg separately.
Okay. Got it.
So you're labeling each instance of that part.
So it's more specific. Okay,
Yeah.
cool. So PartObjaverse-Tiny is giving us a way to test both that broad, like, categorization,
Right.
and then the super fine-grained detail as well. It sounds like the perfect place to really see what SAMPart3D can do.
Exactly. It's a really tough testing ground, and the results are really impressive.
Okay, tell me the good stuff.
So SAMPart3D outperformed all the existing methods, both in terms of accuracy and in terms of being able to control that segmentation level, like how much detail you want.
Wow.
And what's really cool is that it even worked well on objects from completely different data sets.
Oh, wow.
And even 3D models that were generated by AI.
That's amazing. So it's not just like limited to the data it was specifically trained on. It can actually generalize.
Exactly.
That's huge.
Yeah, it's a big step forward. Okay, but let's shift gears for a second.
Okay.
And talk about why this matters.
Yeah, like why should our listener, like why should they care about all of this?
Now, imagine being able to just like click on any part of a 3D object.
Yeah.
And have it instantly segmented.
Okay.
Like that opens up so many possibilities
Yeah.
for design, for editing, for gaming. I mean,
Yeah, I can see designers using this to like tweak specific parts of 3D models, or game developers, making these incredible interactive experiences.
absolutely.
Yeah.
And then there's part level editing.
Okay.
Which is really cool.
What's that?
So that's where you can actually change the material or the shape of a specific part, like really easily.
Oh, wow.
So imagine you're redesigning a car dashboard, or you're experimenting with different chair armrests.
Yeah.
You can do all of that in a 3D environment, like so easily.
It's like having a digital sculpting studio, basically.
Exactly.
That's incredible.
Yeah.
And the paper also mentioned like using SAMPart3D to improve like what they call 3D understanding for robotics and autonomous navigation.
Right.
Can you talk a little bit more about that? Like, what does that even mean?
Yeah. So imagine robots that can not only perceive the 3D world, but they can also understand the parts of objects.
Right.
Like how they relate to each other, what their functions are.
Yeah.
This could revolutionize how robots interact with their environment,
Yeah.
They could perform tasks with much more precision.
Right.
Maybe even a little bit of common sense.
You know, that's pretty incredible. Okay, so we've talked about like how it works, why it matters, but the paper also goes into detail about like how SAMPart3D was actually trained.
Right.
And there's this whole section on distilling 2D visual features to a 3D backbone. And honestly, that sounds a little bit intimidating. Yeah. Can you break that down for us? Like what does that even mean?
Yeah, so it's actually a really clever technique, and it goes back to what we were talking about earlier about how SAMPart3D uses existing 2D image recognition models.
Right.
So they use this technique called distillation to basically transfer knowledge from those 2D models to the 3D backbone.
Okay.
It's like they're teaching it how to see in 3D.
So they're using the 2D models as like teachers.
Exactly. It's like showing the 3D backbone an object from multiple angles.
Okay.
Like let's say a chair.
Yeah.
You show it from the front, the side, the top, and you're basically saying, this is what a chair looks like. And by seeing these 2D views, the 3D backbone learns to recognize the 3D structure of the object.
Interesting.
Yeah.
Okay, so they specifically chose DINOv2 as the 2D like teacher model.
Right.
What's so special about that one?
Well, DINOv2 is really good at extracting features from images.
Okay.
Even without text labels. And that's really important for SAMPart3D because remember, it's doing zero-shot learning.
Right.
So it needs to be able to learn from data that doesn't have all those labels.
Got it.
And the researchers, they experimented with different 2D models.
Okay.
And they found that DINOv2 was just the most effective for this particular task.
Okay, so DINOv2 is like the expert guide showing SAMPart3D the ropes of the 3D world.
Exactly.
Love it. And then they even split this whole distillation process into 2 stages, right? Like there's the large scale pre-training that we talked about earlier.
Right.
And then there's sample specific fine tuning.
That's right, yeah. So during fine tuning, the 3D backbone takes those insights that it got from the 2D model.
Okay.
And then it uses that to focus on a specific object.
Right.
And really start grouping those points into parts.
Yeah.
And even controlling that level of detail like we were talking about before.
Okay.
So that scale condition grouping comes into play again.
It's amazing how they've combined all of these different like approaches to create something so innovative.
Yeah, it's really clever.
Now, did they mention any like limitations of SAMPart3D or areas where they think, you know, future research could focus?
Yeah, they did mention a couple of things. One limitation is that it relies on SAM, which is another model that's really powerful for 2D image segmentation.
Okay.
And SAM is used to kind of generate those initial 2D masks.
Right.
But if SAM makes a mistake, that error can kind of cascade through the whole system.
Yeah, that makes sense.
So, you know, if we could improve the accuracy of those initial 2D masks, that would really benefit the whole system.
Okay, so that's one area for improvement. What about other limitations?
They also mentioned the computational cost.
Okay.
Especially during that fine-tuning stage.
Okay.
So, you know, it can be pretty computationally expensive to train SAMPart3D.
Right.
So future research could focus on maybe developing some more efficient training methods.
Okay.
But even with those limitations, I mean, SAMPart3D is still a really big step forward.
Yeah, it sounds like it's really pushing the boundaries.
Absolutely.
I'm curious to know more about how they like actually tested it in real world application. Like, did they actually try using it for any specific tasks?
They did. They explored a couple of really interesting things. One of them was part level editing, which we talked about earlier. Yeah, you can like change the material or like the shape of a specific part of a 3D object.
Oh, yeah. So like swapping out the material of a chair's legs or like adjusting the curve of a car's fender.
Exactly. Yeah. It opens up so many possibilities for like product design. You can do rapid prototyping and like experiment with different things in a 3D environment.
That's amazing. Like every designer's dream come true.
Right.
And then they also explored interactive segmentation where you can just like click on a part of a 3D object and it's like, boom, isolated.
Yeah. They'll be so useful for 3D modeling and animation, you know?
Yeah.
Imagine you could just select and like manipulate parts of a complex model without having to do all that tedious work of like manual tracing or masking.
Yeah, that would totally streamline so many people's workflows.
Yeah.
That's incredible. And it would just like unleash a whole new level of creativity for artists and designers. And they even took it a step further and explored using SAMPart3D to improve 3D understanding in other fields like robotics.
Yeah. I mean, can you imagine robots that can not only see the world in 3D, but also understand like the individual components of objects, like how they relate to each other, what their potential functions are? That could lead to robots that are so much better at manipulating objects and navigating complex environments.
That's mind-blowing. It's like SAMPart3D is bridging the gap between just perceiving the 3D world and actually understanding it.
Yeah, that's a great way to put it.
Well, I think we've covered a lot of ground today.
We have.
From the technical details of how SAMPart3D works to its potential impact on so many different industries.
Yeah, we've unpacked how it works, explored all these amazing applications.
And really highlighted why this research is such a significant leap forward.
Definitely.
I mean, it's clear that this technology has the potential to reshape so many things.
It really does.
It's like how we design, how we create, how we interact with the 3D world. It's really exciting stuff.
Yeah, and I think as with any groundbreaking innovation, it's really important to stay informed and engaged.
Absolutely.
As this technology develops.
Yeah. So to our listener out there, we encourage you to delve deeper into the source material and keep exploring the ever-evolving world of knowledge.
Absolutely.
Until next time, happy exploring.